One of the National Virtual Conference on Emerging Trends in Applied Mathematics. Here I am to introduce Dr. Paul Isaac, who is going to chair this session. Here, I'm so happy to invite Dr. Paul Isaac, sir, to paper presentation sessions, which are going to be held now. For saying about Dr. Paul Isaac, sir, he is the HOD and professor in Department of Mathematics in Bharathmada Trikakara College, and to his honor, he has presented and chaired a number of invited talks and also in many other sessions regarding conferences and which is regarding international and also national level conferences. He is a PhD holder and he's much interested in terms of fuzzy sets like that. So I hope Dr. Isaac sir will be telling tomorrow about fuzzies during tomorrow's live session of second day of the conference as an invited talk. And now here he is to chair this session of paper presentations. Here we have nearly 3 presenters and hearty welcome to Dr. Paul Isaac on behalf of the Department of Mathematics, St. Thomas College, Thrissur, and IQAC St. Thomas College, Thrissur. Here, we are happy to have HOD, Dr. Saju M.I. sir here. I'll just hand over the mic to Dr. Saju M.I. if possible, to tell a few words of welcome to Dr. Paul Isaac officially for this presentation session. Over to Saju sir. Hello, Saju sir. Can you just tell? Okay, I think there is some technical problem. Previously also it was a bit difficult to connect. Can we just start with sir? Hearty welcome on behalf of the college for chairing this session. Can we please begin? Over to Sabu to say about the paper presentations which are happening. Please call the numbers, the first candidate. Over to Sabu.
Good evening to all. Hearty welcome to Dr. Paul Isaac sir. Our first presenter, Abubakar P., Assistant Professor, Department of Mathematics, Government Engineering College, Palakkad. His topic is Advanced Encryption Standard, a tool for symmetric encryption. Welcome, sir, for the presentation.
So, shall I start?
Okay, start. Are you a research scholar or just?
I'm working as an assistant professor in Government Engineering College, Palakkad, and I'm doing research in St. Thomas College as well.
So, is your date, Sister Julie Andrews, Doctor?
No, I'm doing with Dr. Vijay.
Vijay, okay.
Yeah.
Then continue.
Sir, is my screen visible?
Yes, yes.
Okay, thank you, sir. Let me introduce myself. I'm Mr. Abubakar, working as an assistant professor in mathematics, Government Engineering College, Palakkad. And I'm also doing research in St. Thomas College. Now, I'm going to talk about the topic Advanced Encryption Standard, a tool for symmetric encryption. So let me talk about what is cryptography. First of all, a cipher is a mathematical algorithm that is used for encryption. Encryption is the process of coding a message, and the process of coding we call as encryption, and the algorithm that we used, the mathematical algorithm that we used for that encryption process is called ciphers. And cryptanalysis is the process of breaking the code. So in order to design a crypto system, a designer should have idea about what are the possible attacks that will come from. So that will come under the cryptanalysis. Now, cryptology, the cryptography and cryptanalysis comes under an umbrella that we call as cryptology. Now, what is the objective of crypto system? Now, there are four objectives for a cryptographic algorithm. The major role in data security. You see, this cryptanalysis, or I mean, the cryptographic algorithms are used for data protection in communication, or maybe that is used for data security while communicating a message between 2 or 3 persons or to a group. So the major, there are four objectives for crypto system. First one is confidentiality. So providing confidentiality is an objective of a crypto system. That means only intended person can read the message. Only those person we are sending the message only can read the message. So that is the one objective, and another one is data integrity. Data integrity means that the only during the transformation, I mean, when we are sending the message, then we have to make sure that data that we send is not modified. So that we call as data integrity. And authentication confirms the origin and integrity of the information. And non-repudiation is a service that prevents an entity from denying a previous commitment or action. That means that once a message is sent, he cannot say that it is not from that person. That we call as non-repudiation. Now, according to the secrecy of the key and algorithm, these symmetric systems are crypto systems are classified into two: symmetric and asymmetric crypto system. In symmetric crypto system, the algorithm is open, but the key that is used for encryption and decryption, there is only one key that is used for both encryption and decryption. That key is kept secret. But in asymmetric type of algorithm, in which we use two different keys, one for encryption and another for decryption. So that we call we will kept as secret, that we call as private key, and another one is made public, that we call as public key. Here the algorithm is secret. Okay, so that's about these symmetric and asymmetric crypto systems. Now, again, I'm going to talk more about symmetric crypto system, since my topic is on a tool for symmetric encryption. So, the block cipher, the symmetric crypto system is again divided into two, that is stream ciphers and block ciphers. So, these are the two modes of operation of the data. That means that if we are encrypting the message one bit at a time or one unit at a time, then we call this that as string cipher. And in block ciphers, the data is encrypted as a block. Usually the block length is taken as 64 bits or 128 bits. Now, mathematically, a block cipher can be defined as a function. It's a Boolean function E from 0, 1 raised to k to cross 0, 1 raised to n to 0, 1 raised to n. And now this is a when we choose a k-bit key from this space, from 0, 1 raised to k, this is a string of length 2 raised to k. Then if you take such a string, then we can define an encryption as ek from 0, 1 raised to n to 0, 1 raised to n. That means that this n-bit string is mapped to another n-bit string, and this is a permutation as well. So being a permutation, it is invertible. So this invertible, this inverse function is the decryption function. So then the basic principles of cipher construction. When a person is designing a cipher, then he should focus on these two concepts. First one is diffusion. This is introduced by Claude Shannon. The diffusion process is making the relation between plain text and ciphertext as complex as possible, and confusion is the process, the relation between the plain text and key is very complex as possible. Then substitution permutation network. Here substitution permutation networks are those algorithm in which a series of mathematical algorithm is used, such the mathematical operations like substitution or permutation are used in series throughout a number of times. Then such crypto systems we call as substitution permutation networks. Then let me talk about advanced encryption standard. Advanced encryption standard. Actually, this is a cipher we call, or this crypto system, this symmetric block cipher is actually called as RANDL. This is declared as advanced encryption standard in October 2000 by the National Institute of Standards and Technology. This is an apex body to determine the standard and technology of a cipher. It is proposed by Vincent Ridgman and John Diamond. Regendal, that block cipher is a variable block length and variable key length, but AES, Advanced Encryption Standard, it is fixed the block length as 128. So we are processing 128 bit at a time. With a variable key length, we can use 128 bit, 192 or 256 bits. So AES is an substitution permutation network. Now, how it is connected with Galois field? That's what I'm talking about. So AES is working on Galois field. Here, we know finite field. Advanced encryption standard is operating on the finite field GF2 power Galois field 2 power 8. We know that a field with 2 power 8 element or 256 element can be constructed by taking an irreducible polynomial of degree 8 in GF2. So that irreducible polynomial that is used for the operation of advanced encryption standard is mx equal to x raised to 8 plus x raised to 4 plus x cubed plus x plus 1. And so you see here, every element in GF2 power 8 can be expressed as a polynomial of degree at most 7. So the elements can be represented as A7 x raised to 7 plus A6 x raised to 6 plus etc. plus A0. So this can be, you see here there are 8 elements here. So each of them, we are taking this coefficient from GF2. So these AIs are either 0 or 1. So this can be represented as a 8 bits or 8 bits or 1 byte. So every element in GF2 power 8 again can be expressed as a as 1 byte. Okay. So that's about the relation. Again, this can also can be expressed as an element of vector space of dimension 8 as well. So now let me talk about the internal structure of AES. Data interpretation or data representation of is one of the most important factor that I'm talking about. Here the data is I told that this the data is represented as 128 bit. We are processing 128 bit at a time. So this data is represented as a 4x4 matrix with each, there are 16 cells, therefore each cell is having 8 bit is occupied. Now, there are 4 major operations in advanced encryption standard is sub-byte operation, then shift row, mix column, and add round key. There are, the number of rounds can be 10, 12, or 14. I told that these operations are applying repeatedly, so that the number of rounds can be 10, 12, or 14 according as the key size is 128, 192, and 256. Then let me talk about some more about the internal structure. The first one is sub-byte operation. Sub-byte operation is working on each byte, each cells of the data. So each byte is substituted with another byte. So here sub-byte means substitution. We call this as a substitution of byte. So each byte is substituted with another byte. So we know that we can express the element into GF2 power 8 or as a byte. So each of the byte having two possibilities. So we are having 2 raised to 8 possibilities with us. So we are having 2 raised to 8 factorial possibilities are there for one byte. So we are taking one of the byte and substituting with that. Now this is the process of finding how that 1 bit is get transformed. So that's this affine transformation. We call this an affine transformation. This affine transformation tells about how a 8 bit is transformed with another 8 bits. Now this is a in operating stage, we are just using this lookup table to substitute which byte is substituted with another one. So here we are having the elements from 0 to F and 0 to F. So as an example, 64, a bit 64 can be replaced by 43 and so on. Then this S box is for, this is an inverse S box, this is for decryption process. Now shift row operation, this is another permutation operation. Okay, here the permutation is obtained by shifting the this is an operation that is operating on each rows of the I told that this element can be represented as a 4x4 matrix. So there are 4 rows. So shift row is applying on each rows. Then there is no shift for the first row. Then there is one shift. There is one left shift for second row, and 2 shift for third row, and so on. So these all are doing to bring a randomness to the data. Now mixed column operation is, again, this is an operation as the name. This is an operation on each column of the state or the data. Here each column of the 4 byte is considered as an element of GF2 power 8 and multiplied by x raised to 4 modulo x raised to 4 plus 1 by a fixed polynomial c of x equal to this polynomial. So the resulting element is we call as the result of the each column. So one of the first column is multiplied with this polynomial modulo, this polynomial modulo x raised to 4 plus 1, and that column is replaced by the corresponding element. Now this is the graphical representation of how this process is doing. I'm not talking that much on this. Now the last step in advanced encryption standard or last transformation is the add round key, which is just we are adding or we are XORing this state with the key. We have a secret key with us. We are XORing. XORing is a mode 2 operation. So this is the final element, final state of the matrix after one stage. There are one stage means one round. Then we are having 10 more round with us. So we will perform this operation again and again to bring fluctuations in the data sets. Now, in order to design a good crypto system, a cryptographically secure crypto system, a designer should know what are the possible attacks that will need to face. So some of the attacks I just listed here. First one is brute force attack and linear cryptanalysis, differential cryptanalysis. In symmetric crypto system, we know that the key is kept secret. Therefore, the attacker tries to find what is that key, or he will derive some information about that key. So the method used for those are brute force attack and linear cryptanalysis, differential cryptanalysis. Here, brute force attack is nothing but we are using k bit key, secret key. Therefore, there are 2 raised to k possibilities. Okay, so 2 raised to k possibility. Here, in this case, if you are using 128-bit secret key, then there are 2 raised to 128 possibilities are there. So, suppose he is having one coded message and he is applying this 2 raised to k possibilities on that and to find some information about the secret key. That method we call as brute force attack. Then linear cryptanalysis, it is proposed by Mastery in 1993. Then here what is doing is an attacker is trying to find a linear relationship between, linear equations in connecting the plain text, that is the original message, and ciphertext, the coded message and the key. So by solving those linear equations, he can derive some knowledge about the secret key. That this method, in simple, this method we call as linear cryptanalysis. And differential cryptanalysis is
Excuse me, sir. Please try to complete within 2-3 minutes.
So yeah, I will complete within 1 minute. I will take only 1 minute. Then differential cryptanalysis is here. An attacker is finding some plain text having a specific difference and which will propagate into some other. Some specific output difference or not. From that also he can derive some knowledge about the secret key. So that method we call as differential cryptanalysis. Now let me come to the conclusion. Substitution permutation networks plays a vital role to establish secure channels in various communication networks and all. I just now listed some of them. My research area is the construction of the substitution box. That's the non-linear component of advanced encryption standard. Also in so many block ciphers. So I'm doing research in that. Now the computer systems are working on binary number system. Now I am just extending my works to the future computers that is working on tertiary number system, maybe non-binary number system as well. So my current work is in that direction. This all I just want to share with you. If you have any question, audience, if any question, I can answer it.
Any questions from the audience? There are only 5 participants as far as I see.
Those all are presenters, sir. All others are seeing in YouTube streaming, I think.
There are only 3 of you listening today. I see 5 of them in the chat box. Anybody can ask question. Anybody can ask question. Is there any question? I think there is no question.
Okay.
So, sir, are you a beginner or about to complete your work?
No, sir. I just started. I just completed. I am a part-time research scholar. So okay. I just started only, and now my work is on progress. I am working on non-binary algorithm. Now the algorithm, almost all algorithms are working on binary number system. Now I am planning to extend that into non-binary systems. cryptographic algorithms.
And your topic is good, and your presentation is also very nice. So congratulations,
Thank you,
and
sir.
thank you for your presentation. Okay,
Thank you, sir.
I invite next
Thank
one.
you.
That is okay. Thank you. Johnny Thompson.
Thank you, Abubakar sir. Next presenter is Johnny Thompson, BSc Statistics Scholar, St. Thomas College, Autonomous Thrissur. His topic is Catalan numbers and their applications. Welcome, Johnny Thompson.
Welcome, sir, and welcome,
You're
Abubakar, sir,
a
and all other
graduate
presenters.
student. You're a graduate student.
Yeah, I first year. Yeah, first year undergraduate.
Is this your project, BSc project? What you worked on?
Not
Catalan
exactly.
number?
Just no, not a project. Just came up with it.
Because of your interest in this Catalan numbers, you just went through it. Eh?
Yes, I came upon Catalan numbers during a preparation for an entrance exam, so I was very interested in them. Yes.
Okay, good.
Yeah.
Then start your
Okay.
presentation.
So I'm Johnny Thompson, and I'm here to present a PPT regarding my journal paper on Catalan numbers. So I'm happy. It wasn't expected that the previous presentators, Abubakar sir, who was specializing in the field of cryptography. So Catalan numbers is something that is very important in the field of cryptography.
One thing I have to tell, please try to complete within maximum 10 or 12 minutes. Okay,
Fine.
start, continue. Okay.
Yeah, sure. Okay, so main application mathematics is in combinatorics, and it's using computer programming and cryptographic applications. It was founded by Belgian mathematician Charles Catalan. So to begin with, let's acquainted with some tools which you'll require to derive the closed formula for nth Catalan number. So the permutation of n distinct objects, distinct starred. So we all know that it's n factorial because the first box has n choices, the second has n minus 1 since you put 1 in the first box, and so on till 3 to 1. Then we would have n factorial permutations. Now we are interested in permutation with repetitions. So assume we are given a sequence of 6s and 9s, and each digit is subscripted. So like all the 6s are distinct, all the 9s are distinct, so every number is distinct. So you will have 5 factorial permutations. But what if the subscripts weren't present? I don't differentiate between the 6s. What if I have all the 6s to be identical and all the 9s to be identical? So as you see in the second last line, we have 2 permutations which are different since we have subscripted them. If I remove the subscripts, they are just 6, 9, 6, 9, 6. The same thing. So we are actually overcounting some permutations which we shouldn't. So let's get to this. So assume 3 6s in their respective places. In this, it's like the first, third, and the fifth places. Now they can permute in their places in 3 factorial ways. So actually, all of those permutations are going to be the same, identical. So we have to bring 3 factorial back to 1 every 3 factorial such.
Excuse me.
Yes.
Johnny Thompson, please maximize your window.
Oh, okay. A minute. I'm sorry. Okay. Fine. Do I need to start from the beginning, sir? Okay, fine. So basically, permutation of n distinct objects in n factorial ways, and then we are interested in permutation with repetitions. So assume we have a sequence of 6s and 9s, and all the 6s are distinct. They are subscripted, and the 9s as well. We would have 5 factorial permutations. But what if the subscripts are removed? Then in the second last line, you see 2 distinct permutations, but actually the subscripts are removed. Like all the 6s are the same and all the 9s are the same. You would have 2 similar permutations, but you overcounted them. So how do you remove them so that we get the correct number of distinct permutations? So in this, like assume they are in their respective places. Assume we have 6 in the first and the next 6 in the third and the next 6 in the fifth places respectively. So they can be permutated in their places in 3 factorial ways. But actually all of those are the same because they are not distinct anymore. So we should be dividing those 3 factor permutation by 3 factorial to get it back to 1. It's just 1 permutation because the 6s are no longer distinct. They are all the same. Same in case of the 9s, we just remove the subscript, they're the same. They have 2 places to permute in. So they would be permuted extra 2 factorial times. We just have to divide it by 2 factorial so that all such permutations go back to 1. So in effect, we initially had 5 factorial permutations, but now to remove the repetitions of the 3 6s, just shuffling in their places, we divided by 3 factorial, and the same to avoid repetition of the 9s, we divided by 2 factorial. And so we come up with a general formula that we have m objects of one kind and n objects of the other. We have m plus n objects in total. They can be in totally in m plus n factorial ways. To remove the repetition of the first kind, we divided by m factorial, and to remove it for the second kind, we divided by n factorial. So we have this m plus n factorial by m factorial and factorial. Note it down in your minds, maybe. So then we have the famous bijection principle, which is like whereas it's useful when you have to count the number of elements in a set and you don't know how to count it, but you can relate it to another set which is very easily countable. So like if I define a relation from a difficult set A to a simple set B such that the relation is 1 1 and on 2, then actually we will have the same number of elements in A as in B. So we just have to count the elements in B, which is very easily countable compared to A. So both of their cardinalities would be equal because it's a 1 1 and on 2 bijection relation between them. Now let's get to the topic. How do we attack the Catalan numbers? How do we derive the nth Catalan number formula? We are going to look at the parenthesis problem, which is very famous. And so you're given same number of open brackets and closed brackets, like say n, okay? And you're supposed to make valid expressions with these brackets. How many valid expressions can you make with n open and n closed brackets? So for example, as given n equal to 2, we can only make 2 expressions. Now, what do I mean by an invalid expression? When you have at some stage when you have more closed brackets than open brackets, like at some stage when going from left to right, at some point you have the closed bracket number greater than that of the open brackets, it's an invalid expression because we just closed a bracket that was never opened. But in any stage, if we have the number of open brackets greater than the number of closed brackets, it would be fine because we could close them later on as we are going leftwards, forming the expression. But if you close an unopened bracket, that is irreversible. So that is what I mean by an invalid expression. And then, so you're given n open brackets and n closed brackets. So by the formula, like for permutations with repetitions, we have n plus n factorial in total. To remove the repetitions of the n open brackets, we divided by n factorial. Remove the repetitions of n closed brackets, we divided by n factorial. So we have this expression. These is the total number of permutations of n open and n closed brackets. They would include the invalid expressions, but we need to find the number of valid expressions. So what are we going to do? We are going to find the number of invalid expressions and subtract it from this. So we get the number of valid expressions. So for the easiness and more comprehensibility, let's consider the open bracket as a +1 and the closed bracket as a -1. So this expression is called valid if at any stage you have the number of +1s greater than the number of -1s. Because if you have the number of -1s greater than the number of +1s, you will have an extra closed bracket. That's a problem, as we discussed earlier. Now consider the set of all invalid expressions A, and it's a sequence of AIs with every AI either being +1 or -1, an open or closed bracket. So let's say at the kth stage is where this invalid expression first goes invalid. Like AK is the extra -1 introduced. Till before that, we have equal number of +1s and -1s, but at AK we have an extra -1. So that is where the expression goes invalid firstly. So now look at the sequence and note that AK is -1, the extra -1. And before that, we have equal number of +1s and -1s from 1 to k -1. So let's say j +1s and j -1s. And then after AK, we had n +1s and n -1s in the beginning. We had given equal number of brackets. So after AK, we would have n minus j +1s and then n minus j +1 -1s, because we have to subtract the extra -1 of AK and the j that has been included in the second bullet point. So j +1 we have to subtract from the n to get the remaining number of -1s in the sequence from k +1 to 2n. Now, after trying hard and trying to find the number of possible expressions that are valid, mathematicians sweat, but in vain indeed. So they had to someone had to come up with this new concept. We are going to relate the sequences in A to another set of sequences B, in which we just reverse the signs of elements after AK. Till AK is the same. After AK, we just make it minus ak plus 1 minus ak plus 2 till 2n minus a 2n. So we just reverse the signs. So bi is equal to minus ai. And now note, ak is still the same. Ak is still minus the extra minus 1. Before ak also it is still the same. We have j plus 1s and j minus 1s. But after ak, we just reverse the signs. So what do we have now? In the previous slide, we saw that we had n minus j plus 1s. But since we reverse the signs, now we have n minus j minus 1s. And then if we look at the next thing, it's the same. We had n minus j plus 1 minus 1s, but since we reverse the signs, now we have that many plus 1s. And then, so let's now count the number of plus 1s and minus 1s in this new sequence B. So as we see, a number of plus 1s is equal to, in the second bullet point, j plus the third bullet point, n minus j plus 1. We have n minus 1 open brackets. And the number of minus 1s in the first bullet point, the extra minus 1, plus, that is the 1, plus the second bullet point, j, plus the third bullet point, n minus j. So the total number of minus 1s or close brackets is n plus 1. And now, why did we just transform this sequence? Why did we map it to another set? Because this set was very not countable. A minute, sorry, I missed the point. Now, look, in this sequence B, we have n plus 1 closed brackets and n minus 1 open brackets. We have more closed brackets than open brackets. There are 2 more closed brackets than open brackets, actually. So any expression in B is going to be invalid because we have more closed brackets than open brackets. At some point, we will be closing a bracket, extra bracket that was never opened, because we have more closed brackets. We have to use all the brackets. And so we'll be closing an unopened bracket, and that would, any such sequence in B would be invalid because we have more closed brackets than open brackets. And so B is very easily countable because every sequence in B is invalid. So now we have to like make sure whether these are all the invalid sequences we have to get. Maybe there are more invalid sequences that are not in B. So to prove the bijection between A and B, we first proved one-oneness. Assume that two sequences in A have the same image in B. The same way we prove one-oneness for any function. Like we assume 2 elements have the same image in the other set, and then you see the second line. That's what we get. Say the AI is AI is, yeah, fine. So two elements have the same image in B, and then we have these sequences. These are the same. These are the images in B they have, and then we are going to perform the reverse transformation of the BIs. We just changed the sign in the previous slide. Now we're going again to we are again going to change the signs so that we get back what was in A. So we just reverse the signs again after AK, and then we get the 2 sequences back. But now you see that AI and AJ are the same image in B implies that AI is equal to AJ. So that's what we learned in 11th and 12th grades, that it's a 1-1 function.
Right, please complete in 2-3
It was a 1-1 function from A to B because
minutes.
AI and AJ to same image implies A equal to AJ. And for ontoness, any sequence in B is going to have a corresponding sequence in A, because we just do the reverse transformation, we would get an pre-image in A. And so we have bijection, and then the number of expressions in A, that's what we have to find, is equal to the number of expressions in B. So we just have to count the set B. And to count the set B, it's easy because we have n minus 1 plus 1s and n plus 1 minus 1s. And so we do the formula for permutation with repetitions. And so we get what is on the screen, 2n factorial by n minus 1 factorial, n plus 1 factorial, which is indeed the number of invalid expressions. Now we have to subtract the number of invalid expressions from the total number of permutations to get the number of valid expressions, which is 2n factorial by n factorial, n plus 1 factorial. Eureka, this is the nth Catlin number. These are the first few Catlin numbers, C0, 1, 2, 3. You can just, a minute, if you want, you could note this down, the formula for the nth Catlin number, 2n factorial by n factorial, n plus 1 factorial. And when you put in the different values, you would be getting this list till 5. Now the applications, like, we wouldn't be counting number of bracket expressions in real life. Why is this even here in applications in mathematics? So it has applications in cryptography and architecture. In architecture, when we have to triangulate a polygon with n sides, it can be triangulated in Cn minus 2 ways. Is n minus 2th Catlin number, where n is greater than or equal to 3. Now the number of dict paths, that is basically upstrokes and downstrokes, such that the path never goes below the line given. So if you take up paths to be plus ones and the down paths to be minus one, at the point where you have an extra -1, it would go down. Same concept. And then the number of binary search trees in computer science and the valid paths of length 2 and without crossing the diagonal, the up paths would be taken to be plus ones and the rightwards paths would be taken to be -1. So if when you have an extra rightwards path than the upward path, you cross the diagonal. Now other applications are finding the number of disjoint codes you can make with given endpoints on the circle, and cryptography to create strong encrypted passwords for files, because Cattell numbers are a bit complex indeed. Formula derivation was hard, you see, and it's very useful in cryptography and also in topographical geometry and computation geometry and computer programming. These are the books I referred to get the content regarding Cattell numbers. And thank you for listening. It means a lot to me. Yes. Any questions? You wouldn't have. Okay.
Any questions from the audience? Any questions from the audience?
Can I just say a comment, sir? Johnny is my student. Actually, he is from first year BSc Statistics. This is Julie speaking, sir.
Not here.
I was just telling him there's a... Okay.
Who is asking the question? I can't
One
hear.
second. Yes, sir. Sir, Mr. Julie Andrews is speaking, sir. I was just putting in the group, there is a conference, and Joni was asking that day itself, can I present, ma'am? So I told you can, if you are coming with the true subject. So he was doing the work within some days, and he sent the paper, and it was very nice. I was seeing the paper, and I was also not knowing much about this Cattell numbers. And I was really excited to see the paper and such a beautiful presentation. I would like to congratulate Johnny Thompson for his presentation.
Yes, the presentation was very nice, and congratulations.
Thank you.
So you continue your work.
Yes, sir. Thank you,
can
sir.
do your work with PhD research in this direction.
Yeah, thank you, sir.
Congratulations once again. Thank you.
Thank you, sir. Thank you.
So I think one more participant, one more
good day.
Yes.
One more presentation is there.
Thank you. Thank you, Johnny Thompson. Our next presenter is K. Soundarya Mohanan, BSc Chemistry Scholar, St. Thomas College, Autonomous, Thrissur. Welcome, Soundarya Mohan.
One second, sir. There is a technical problem. She's getting connected. Just getting connected. Yes, it's coming.
Problem. Yes. Soundarya, present your matter in 10 minutes.
Yes, sir.
Don't take more than 10 minutes.
Yes, sir.
Soundarya Mohan, let us start our presentation.
You can start your presentation.
Yes, sir. Is the screen visible? Sir, is the screen visible?
Yes. It is coming.
Yes, visible. You please make it full screen view.
So, good evening, all. I am Soundarya Mohanan from the Department of Chemistry, St. Thomas College, and I am here to talk about integrals.
It is not audible. Soundarya Mohan. Not audible.
Network problem.
Excuse me,
issue.
sir,
Problem.
there is a small
Okay.
network issue.
Okay. Left eye.
Hello, sir. I think there is a network issue. What we have to do, sir? Is there some other possibility like that? We can shift it to tomorrow. We'll try like that.
Okay.
She was telling me there is some network issue like that. She's trying, but
We
still it's
can,
not coming, it seems.
can postpone tomorrow, no problem.
Okay, sir. Tomorrow there is nearly 8.
It's,
It's 8 to 10, but still. Okay, we'll try tomorrow, sir. Is it okay?
tomorrow we can postpone tomorrow.
Okay, sir.
Just tell all participants to stick on time.
Yes. Yes, 10 minutes like that. No, sir.
10 minutes maximum. 10 minutes.
Okay, sir.